RB3, what's going on? RB3. RB3. Ah, yeah. Hey. Whoa, teacher's pet. Wow. RB3's loaded. Insane. Hey, see what's going on. Ah, good to see you. Bro. Oh no. Oh no. Not good. Okay, Crow. Okay. Okay, you're really gonna... Okay. Your computer broke? Oh, that's why... So that's why you, So, bro, maybe you slipped when you were typing, and so that's why you accidentally redeemed, like, till heart explodes. Okay, now I understand. Okay, you didn't mean to do that. Okay. Okay, that makes more sense. Oh yeah, that's probably what you meant. Yeah. Oh wow, look at that. Bro is teacher's pet. Wait, 2 teacher's pets. Incredible. Incredible. Yeah, Jax. Whatever message you get from this stream, that's what I intended. Awesome. Great. As long as it's a positive message. Amazing. Teacher's zoo. Yeah, the value of teacher's pet, yeah, plummeted when I made 2 of them. Awesome. I'm glad that you have a special notification. Alright, now let's see. Teaching today. Make sure I understand what I'm teaching. Teaching this, and this. Okay. Not bad. Be easy. That's right, Crow. You did the math. Crow, you are on the up and up. You know that? I've noticed great improvement in your... Whoa. RDL, that is uncalled for. Insane. That is just really insulting. Okay, here we go. Oh, where's my Spotify? Hold on, folks. I need to do that random background music. All right. So, what's going on? Everyone, come on in. Have a seat, class. Seem to be here. RB3, you're a good student. You're a teacher's pet, so that makes sense. Okay, let's start. Ring theory. That's our new topic. Class. Chapter 13. Or 14. Whatever. 13 or 14. In the book. Please remember our convention when reading the book. Our secret convention was that all rings have a 1. Great. Okay, so today's topics is important, and I'll try to cover three things: the concept of an integral domain, the definition of a field. Fields will be the main object of study next semester, and towards the end and the last part of this semester. Okay, so fields are just certain kinds of rings, and I'll define them today. And then I'll do some simple theorem, which is a little bit extremely simple, just because everything else is a bunch of definitions. This is just definitions. Definitions and examples and non-examples. That's the kind of situation we're in right now. So I should just sprinkle in a theorem, okay? But that's overstating what it is. Okay, so ring theory. Just like in group theory, you should always ask. You should keep asking every time a week goes by, what the heck is group theory about? And in the beginning, group theory starts off saying things like, how do we codify the concept of a symmetry? And how do we manipulate symmetries? And what are the rules of that game? You end up with group theory. And then you can study it on its own, and it becomes this amazing, wild zoo of beautiful different kinds of groups, and you can go try to classify them, try to understand every single finite abelian group, which we did. And what about all finite groups? Kind of impossible, etc., etc., etc. You try to find anatomical pieces of groups, etc. Okay. Ring theory. Where does ring theory start? Ring theory, what is it about? Ring theory asks if there's more types of number systems than just the integers. Meaning, is there a mathematical structure that codifies the notion of integers? So Z is the sort of first object that gives rise to the study of ring theory. We're studying generalizations of Z. That's how you should think of it. Okay, so integral domains. Let's start. Okay. All right. So, an integral domain so here's my definition. Is a commutative ring such that whenever A times B equals 0, then A equals 0 or B equals 0. Okay? Who was that? Who was this? Oh, hey, Odyssey. What's up? Okay, so an integral domain is a commutative ring, which has a unit, remember, always, such that it has a identity, a 1, such that whenever A times B equals 0, then A equals 0 or B equals 0. You're used to this. You're used to this being true about the integers, all right? But not all rings are integral domains. Not all commutative rings are integral domains. So let me show you an example right away. me show you an example right away. Okay. Let's do Z mod 6Z. All right. Notice in Z mod 6Z that 2 times 3 is 0. Okay, but 2 and 3 are not 0. I could also do Z mod 4Z. Okay, you get 2 times 2 equals 0. So 2 and 2 are not 0. But okay, so that's what integral domains are trying to get away from, this weirdness that you see in these kinds of rings. Z mod 5Z, on the other hand, is an example. Okay? Awesome. Okay, Kappa. Okay, very good. Very funny. Let's just make it all political, Kappa. Everything is just hashtags and... Oh, my God. All right. Okay. Let me show you another characterization of integral domain. Okay. Suppose, so this is gonna bring up a sometimes useful tool. So just like we had tricks of the trade last time in group theory, ring theory has its own kind of tricks. Okay, here's another way. It looks weird, but let me just bear with me. Here's another way of characterizing an integral domain. Suppose. Okay. So let me start a little bit earlier than I intended to. Okay, so let's do a definition. Okay, this definition is super general. Okay. An element of a ring commutative or not, doesn't matter. An element of a ring is called a zero divisor. Okay, notice how this is phrased. If the function m sub a, actually let me write it out more. Let me denote it. Mult a from R to R. If the function multiplication by a from R to R, here's the formula. An element goes to a times the element. An element is called a zero divisor if this function is not injective. Okay? To say it another way, oppositely, called a non-zero divisor if multiplication by a is injective. Okay, so the multiplication by a just means take an element in the ring and multiply it by a. That's a new element. That function. We're asking whether it's an injective function or not. That's the difference between, the definition-wise, between an element being not a zero divisor versus being a zero divisor. Why is it called zero divisor? Let's take a look at this. Look carefully at this multiplication by a map. This is a group homomorphism. So what does that mean? What does injectivity mean then? That's the same as kernel is bigger. No, kernel is 0. Injectivity means kernel is 0. Let me write that out. It means whenever a times something is 0, then b is 0. And let me write this another way. There is no non-zero element such that a times b equals 0. This is why we call such an element a non-zero divisor. It's an element that does not, interestingly, divide 0. Which interestingly divides 0. An element for which there's a non-zero element. When you multiply, you get 0. That's what a zero divisor is. A zero divisor is one where there's some weird non-zero other element, possibly itself, that when you multiply, you get to 0. Okay, so elements come in two types. There are zero divisors, and then there are non-zero divisors. And the way you can distinguish between those two is using simple language from before. Look at the multiplication by a map. It's either injective, that means you're a non-zero divisor, or it's not injective, and that means you are a zero divisor. Okay? So that's the concept of an element that weirdly is a factor of 0. Okay, so example. 2 is a zero divisor. BMP, is it true that every rung is the ideal of some ring? Okay. Actually, AC? Yes, it's true. I think it's true. In fact, there is a standard operation called, I forgot what it was called. It's called like oneifying or ringifying or something, where you take a rung and you just adjoin an element. And then you know, it's one of these situations where you have to make sure that the construction works, but there's a way to minimally adjoin a new symbol to a ring, which serves as 1. serves as a 1. And so if you look at that procedure, I forget how it works, but there's a way to ringify a rung by formally adjoining an element. And I think the rung is then an ideal in the ring. I have to think about that, but I think the rung is an ideal in that ring. In the ringification of the rung. I have to check. I have to go back and look at that construction. But yeah. All right. 2 is a zero divisor. 2 is a zero divisor in Zmod 6. 3 is a zero divisor. Yeah, these are good questions. Will that make the rung a maximal ideal? Yeah, I don't know. Possibly. Probably. I don't know. I have to look at the method of adjoining the one. You just adjoin a symbol called E, and then you have to enforce some relations. But yeah, I have to check. I have to see how that works. Okay. Anyway, so zero divisors. 0 is a zero divisor. According to injectivity and non-injectivity definition. Okay, so 0 is a zero divisor. Okay, now people who are, I am very smart people, they will object. There is one particular ring, folks. So what I just said is mostly true. 0 is usually a zero divisor. Okay. In any ring, except for one ring. There's one insane troll ring, okay? Which we're not going to talk about. We're just not going to talk about this ring very much at all, okay? There's a troll ring. The biggest troll ring. It's called the zero ring. It has one element. And that element has to be 0. But that element is also 1. And here, you want to write out the multiplication and addition tables. And the thing about, yeah, that's a wrong. Yeah, this is wrong. Yeah, this is the wrong. It's just such a silly ring, okay? And this sentence, class, don't worry about this. This sentence, 0 is a zero divisor. It's false for only one ring, namely the wrong. Because multiplication by 0 is still injective for this ring, for this wrong. Okay? So forget about it. You know what a zero divisor is when you see it, all right? 2 and 3 are zero divisors in Zmod 60. So what's an integral domain? A commutative ring. If every non-zero element is a non-zero divisor. Or just state it the other way. Or if there are no non-zero zero divisors. Okay? And then you can prove very simply, easily. Go ahead and, as an exercise, show if in an integral domain you had a times b equals a times c, where a is not 0, then b equals c. Okay? So you can divide out, so to speak. You can cancel out you can cancel out a for any non-zero a if you have such a situation in an integral domain. Hint is just look at distributive. Just look at that equation and use the non-zero divisor constraint. Okay, so in integral domains, you can cancel out non-zero numbers from either side of an equation. That's what integral domain is really allowing us to do. These are nice rings. They are closer in spirit to what we saw in the integers, and they kind of throw away Z mod 6Z. Weird rings like that. They are like integers. They're less like Z mod 6Z. Awesome. Let me do tons of examples. Z mod PZ, any prime. Okay, integral domain. Let me show you an example, a type of example that's very, very important that we haven't talked about yet. Z adjoin X. This is the polynomial ring. So it's one variable with integer coefficients. Plus and times are just adding and multiplying polynomials. Like in 6th grade. Check your 6th grade notes. Okay? All right. Okay, so Z adjoin X. So like 3 plus X squared 3 plus 2X squared minus 4X plus 9. This is an element. This is an element in Z adjoin X. Okay, this is an integral domain. Why? Students, think about this. Are you able to prove that this is an integral domain? Why is this true? Okay, great. So let me show you another example. Q adjoin X. This is a polynomial ring with coefficients which are rational numbers. R adjoin X. C adjoin X. Okay, you can take coefficients, rings, slap on a variable, and talk about polynomial expressions with those kinds of coefficients. All three of these are integral domains. Of course, the integers are an integral domain. Here's another example. Z adjoin I. The Gaussian integers from last time. This is an integral domain. Class, I leave it to you to ask, to figure out why. You could just use the definition, but there's a slightly more clever way to go about it. Okay. Awesome. So, integral domains are all over the place. They arise naturally, and they exhibit a certain nice quality, cancellation, that is convenient and makes more sense to human beings than random rings like Z mod 60. Okay, so that's the bottom line for integral domains. We like them. Okay, so now, after we have the definition of integral domain, okay, Rx and Rx are pretty similar. We have named the ring R because Rx. Oh, but this is R. This is bold. I don't know what's going on. Okay, anyway. All right. Integral domain, just a definition. There's a particular kind of integral domain that's ubiquitous in mathematics and will be the main focus of study in Galois theory. And those integral domains are called fields. Before I go to the definition of a field, I need to do another definition. Okay. So the second thing. Fields. All right, before we start fields, let's talk about definition. Okay. Prelim definition. An element in a ring is called a unit. Called a unit if there is an element B such that A times B equals 1. In other words, it's an element that has a multiplicative inverse. Like 1 over A is still in the ring. Okay, so an element is called a unit if it's multiplicatively invertible. Okay, so for example, plus and minus 1 are units in Z. And they're the only units. Right? 2 is not a unit because 1/2 is not there's no integer that when you multiply by 2 you get 1. So that's what a unit is. Here's an example. Every non-zero fraction is a unit in Q. Everything that's not the zero element is a unit in Q. All right? All right. What else? Example. Every non-zero real number is a unit here. 1 over pi is a real number. every non-zero complex number is a unit in C. Example. Every non-zero element of Z mod 5Z is a unit. See if you can. 2 times 3. For example, 2. 2 times 3 is 1. Go and do all the rest. Example. Two is not a unit in Z mod 6Z. Neither is 4, neither is 3. In fact, the only units are 1, 5. Okay, so now we know what a unit is. So now we can say what the definition of a field is. A ring is a field. Yeah, well, this is terrible. This is a terrible way to write it. A field is an integral domain such that every non-zero element is a unit. Okay, this is what you'll find in the book and in most books. Okay, but there's a slight problem with this definition. Okay, there's a slight problem. And many books will not want it, they won't even talk about it. Okay, so one thing you should always exclude in this thing is, here's a convention. It's not a convention. What you should add in the definition is that a field is an integral domain with at least 2 elements, such that every non-zero element is a unit. Okay, you need to exclude the wrong. Exclude the zero ring. Okay? That's not a field. Forget about it. That's stupid. Don't think about the zero ring. You won't get anywhere in life. All right? Fields, actual ring. Every non-zero element is multiplicatively. You can do reciprocals in a field. That's what a field is. So let's go back to these examples. This, not a field. This, a field. This, the field. This is a field. This is a field. This, not a field. It's very easy, folks. These are just simple definitions. You should be able to tell whether a given ring in front of you is a field or not. That's the kind of stuff I'm going to ask this coming exam next week. Okay? On Monday or Sunday. Is this an integral domain? Is this a field? What about this weird ring that I just made up right now? Is this even a ring? That's the level of definitional exam that you're up for on that is awaiting you on Sunday. Okay. All right, so how many fields do you know? I'm not going to get to the simple theorem. It's a silly theorem. We'll talk about it next time, very briefly. It was just, forget about it. How many fields do you know? Okay, there's Q, there's R, C. Okay, there's actually way more. Way more. These are the ones you learn, right? This is 6th grade, 7th grade, and this is you learn these things. Okay, there's way more. Okay, just like there's so many groups out there. It's not just cyclic group, dihedral group. No, there's way more. And I opened the weird door at the very end of group theory. GL3 of F2. The heck? Completely unlike all the traditional examples we'd been seeing up until then. Came out of left field. Yeah. Way too many groups. Similarly, when someone says they have a field, it's just a wide zoo of possibilities. And we want to study all of them as much as we can. It's awesome. Okay? It's not just Q, R, and C. Look, Z mod PZ for any prime is a field. Okay? You learned this in 3613, so I'm not going to spend too much time on it. We can talk about it in Discord if you really want to see a proof of it. Okay. So Zmod PZ, or revisit a proof of it, remind you of a proof. Zmod PZ is a field. And these are finite. What does it mean for a ring to be finite? It's finite. Okay, let me show you a weird one though. This is not it. This is also not it. Okay. I'll show you a weird field. It's called Q, and then you put, for some reason, you put round parentheses. And then you put this thing called I. What is it? This set. What is addition and multiplication? The same as with complex numbers. This is a sub-ring of C. What do you like? Here's an element, 1/2 plus 3i. I claim that this element has a multiplicative inverse. You do this. Multiply by conjugation. Pay attention to this little step right here. Right here. In other words, there is a rational plus a rational times I, which is the inverse of this element. Secret is multiply by conjugate on top and bottom. That's what makes it tick. That's why this is a field. This is a field. It's not C. It's not Q. It's somewhere in between. It's not R. Okay? More. There's more. Even more. This world is crazy. The world of fields. Look at this one. Strange example. You start with Z mod 3Z. That's a field. Because 3 is a prime. Then? Okay, this is weird now. What are we doing here? This is very strange. We're gonna take this, we're gonna include a symbol called I. This is just a symbol. And here's what this ring is as a set. And how do you multiply two elements? Here's the multiplication. Adding is adding the A's and the B's. Just exactly like you do it in any other situation where you have a concept of I. I times itself is the element -1, where you're thinking of -1 as an element in Z mod 3Z. Or 2, if you'd like. Same element. Same coset. Same rep. So I squared is 2, or -1, whichever one you'd like. That's what we mean by the symbol I. Do FOIL. And use I squared equals -1. That's how you multiply. Okay, but this is a field. How do you know it's a field? I want you to go check. Every single element has a multiplicative inverse. Every single non-zero element. So this is a field that has 9 elements. It's a field with 9 elements. It's not Z mod 9Z because Z mod 9Z is not a field. Amazing. This world is crazy. Crazy world. Okay, I'll end just with a side note. Just for mystery. Oddly, if you try the same exact game, you will find it is not a field. Okay? So there's something bizarre going on here with the concept of adjoining, including a square root of -1, the additive inverse of the 1 element. There's some weirdness, mystery. And we're going to learn all about these kinds of things as the days progress. All right? So for now, collect all the fields you can. Go and try to create as many fields you can. Make sure every non-zero element is invertible. Check it by hand. That's your bulking up of examples that's required as this class proceeds. Why would you abstract 9 as Z mod 3Z? I wouldn't. I'm just saying that this is a field, this is a ring that has 9 elements. Okay? This is a ring that has 9 elements. And maybe you think, okay, oh, then it's got to be Z mod 9Z. No. Maybe you think it has to be the product of Z mod 3Z times Z mod 3Z. I haven't talked about the product of 2 rings yet. I'll do that tomorrow, I guess. I mean, Wednesday. It's simple. It's also not that, because the product of 2 rings will never be a field. So it's some bizarre extra ring of 9 elements. It's just showing the diversity here, folks. We're in a similar situation as, oh, what are all the groups? Just dihedral groups? That's it? No, it's unbelievably rich. Even when we impose heavy restrictions like fields, there's just too many. I can't list them all. We're gonna have to start mapping them out with different kinds of properties. Observing some things are true about some fields and not about others. But that's the shape of the subject moving forward. We're still at the zoology stage. Just look around, look at rings, look at fields, look at these. But then what's there to say? You'll see. Okay. Please remember, class, collect as many examples as you can early. Ponder them. Test definitions against your examples. Read the book with our convention. And I just want to emphasize, class, that the study of fields is exactly where you will find the answer to this mathematical gem. Why isn't there a quintic formula? Why was there a quadratic formula? Why is there a cubic formula? Why is there a quartic formula? Why is there no quintic formula? All of those questions are ultimately questions about the structure of certain kinds of fields. That's what happens next semester. So we need to bulk up our understanding of fields as the last month of this semester, starts coming to a close. Okay. So Wednesday. More about fields, and I'll prove a stupid little theorem. It's not really a theorem. It's just to see an argument rather than just zoology. Let me look at chat now. What happened in chat? Finite means finite. You heard it here first. That's right. Algebraically challenged. That's right. It's anonymized. Q anonymized. Kappa, that was disgusting. Credits. AC, keeping them in line. And there was Kappa. Different. Okay, but we like all people here. Okay, don't worry. RDL, bringing the wisdom. I see you're spitting facts in there. Else. Ebok, new person. Gotta give attention to the new people. That's why they'll keep coming. Don't give them the dopamine hit, they're gone. All right, where's this? Who's this? Oh, that's Davis. It doesn't come out. Weird blue color. Everybody, really. Crow, arbitrary. Arbitrary. Teacher's pet. Johnny Scarlet? Who? This gotta be a bot. Is this a bot? Wait, why does Koshi need a credit here? No. Here, no. This is Dedekind. This is another. These are the ring theorists. Field theory. Galois. Abel. Not nearly as on everything as other people. No. He's like Dedekind. He's like Galois. No, they're different territories still. Yeah. No. Oh, you're a new viewer? You like the lecture but don't understand a lot. Okay. So the fact that you wrote that means you want to be included in this? Is that right? Right in Swan? So you're begging to be in the credits. Okay. Is that accurate? That's all I know about you right now. Okay. Who else? There's Johnny Scarlet also. Okay. Fluffy! Good to see you. Everyone go check out Fluffy. Friend of ours. Friend of the stream. How do I do this? Oh my god. S-O. S-O. Friend of the stream. Work? Yeah. Alright, Fluffy. Have fun. I'll juggle for you real fast. Okay, I'll juggle for you real fast. Fluffy, redeem juggling. Here you go. Do this real fast. Make it really memorable. Real memorable. Alright, class. Integral domains, fields. They're mostly definitions. When you face a general definition in a math class, it is your job to try to find as many examples, understand as many diverse examples as you can. That is your primary objective when that happens. All right? Awesome. We're in a definitional place, not a theorem place right now. Just like early group theory days, back in the good old days. Okay, ready? Let's go. I gotta go learn what is a have no idea what I'm teaching today. What comes after? Okay, well, saw it here. I really need to go figure out what the heck I'm gonna say. My calculus. So thanks for. Oh, let me roll the credits here. Oh yeah, no problem. Thanks for redeeming that, Johnny. You see how the channel points work? Frightened Swan. That's how it works around here. Could you tell a little bit about yourself? Are you a PhD student? I used to be. I used to be a PhD student, but now I'm a well, assistant professor. Hopefully, a professor next year. Okay. He is. Yes. Yeah. Yes. I'm a PhD student. I'm no longer a PhD student, but I'm still a student because there's always more to learn. What a great ending. Wow. It's like PBS in here. There you go. Will Davis has the right attitude. I'm not a PhD student. I'm a student with a PhD. The more you know. Reading Rainbow. All right, folks. Alternating series.